Lesson 11:8. Interference, Huygens principle, and Young's double slit experiment. Light is both a wave and a particle. We were using the ray tracings. That's like particle. It goes straight, bounces off, goes back. We're also going to talk about the wave character. When it interacts with an object several times its wavelength, light acts as a ray. When it interacts with smaller objects, it acts as a wave. It's kind of this dual character. When light hits medium from a vacuum, it slows down, but the frequency remains the same. Speed of light is frequency times wavelength. Speed is our speed of light over our index of refraction. Therefore, our speed should be the frequency times the wavelength divided by the index of refraction. So our new wavelength, the wavelength in a medium, is the wavelength in a vacuum divided by the index of refraction. Huygens' principle says, every point on a wavefront acts as a tiny source of wavelets that move forward with the same speed as the wave. Their wavefront at a later instant is the surface that is tangent to those wavelets. So you can see in the picture, we've got this big wave coming, and it hits. We just pick these 5 little points here, and they become their own waves. And then the overall wavefront now is this combination of their little wavefronts. Well, in 1801, Thomas Young showed that 2 overlapping light waves interfered and was able to calculate the wavelength. So what he did is he used 2 tiny little slits and shone light, the same light through these little slits, and they interfered with each other, which showed that the light spread out. So how it goes, we have light source here, light source here, and they each produce their own wavefronts, as are marked by the little circles. Where they meet, where a crest meets a trough, like right there, we get a maximum. Crest meets crest, you get a maximum. Where you get a crest meets trough, like right there, you get a minimum. And you get this pattern on the wall, like over here in section C. What's really interesting is, so light is a single photon. There's a bunch of photons, those are the particles, but they also are the wave. In this experiment, they've done it now with, so it's single photons. That was back in the 30s. Single photons, and it still interfered, which is really weird because you only have 1 at a time. So it either goes to the top slit or the bottom slit. So it seems like it should just go straight through and not interfere because there's nothing to interfere with. But it still made the pattern. But then they put a little detector on the 2 slits to figure out which one the photon of light was going through. You know what happened? This whole interference pattern went away, and it just became 2 dots on the wall. It's like the photons, the light knew it was observed and then behaved differently. Really weird. We're not going to really get into that because that is quantum mechanics, and that's beyond what we're doing in high school physics. If you're curious, you can read about it. There are many books out there written well, for the general person about quantum physics. All right, let's use some geometry to come up with some formulas. All right, so there's a bright fringe whenever the length from the 2 slits, when that difference is a whole number of wavelengths. So that you have crest and crest. So you have a whole wavelength to get to the next crest. So the difference in path lengths from the 2 holes to our point needs to be a whole wavelength, like here. So here's one path, there's our other path. To get a bright spot up there, this distance here needs to be a whole number of wavelengths. You'll get a dark spot where it's a half of a wavelength. So a half, or 1.5, or 2.5. So it's m plus a half number of wavelengths. The brightness of the fringes varies. The center fringe is the brightest and decreases to either side, because more light goes straight than bends. Picture A. Rays from the slits S1 and S2 make approximately the same angle with the horizontal. Strike a distant screen at the same spot. So I know that these two rays here are not parallel if they strike at the same point. However, let's say they're almost parallel. Close enough that we can estimate that they are parallel. Picture B. The difference in the path lengths must be, okay, so here's the difference in the path lengths, and that's perpendicular, so that makes a right angle. Hypotenuse is D, so this is opposite over and hypotenuse. So that'd be sine. We could say sine of our angle is the opposite over hypotenuse. So our difference in lengths equals d sine theta. For picture C, the angle is the angle at which the bright fringe occurs on either side there. So, oh, hey, we could use trigonometry there also, since that gives us right angles. So our difference in path length is d sine theta, and our bright fringe occurs when our difference in path lengths is some whole number of wavelengths. So if we substitute that and solve for sine theta equals m, which is some integer, wavelength over the d. D is the distance between the slits. And the dark fringes, the difference is we're adding a half to the m. So remember, this is bright and this is dark. A laser beam of 630 nanometer wavelength goes through a double slit with a separation of 3 micrometers. If the interference pattern is projected on a screen 5 meters away, what is the distance between the third order bright fringe and the central bright fringe? So I'm going to draw some geometry. My laser's there. It's 5 meters away from our screen. My screen's down here. In the middle, M is 0. That is the bright spot 0. And down here is M is 3. That means it's the third order bright spot. So it's the third bright spot away from the center. And we want to know that distance. All right, so we can use this little formula we just developed. M would be 3 because it's the third order bright spot. It's third order right there. Highlight. So M is 3. We have our wavelength, 630 nanometers. That's times 10 to the negative 9. And our separation, our D, so this is here, that's the D, is 3 times 10 to the negative 6. I need the same units, so I'm just going to make them all meters. Do inverse sine, and we get our angle of about 39.0501. Now if we look at our little triangle that I drew, we see that we could just use tangent there. So tangent of the angle is the opposite, x, over the adjacent, 5. Multiply both sides by 5 and run it through your calculator, and that separation distance is about 4.06 meters. Do your best. Don't let other work interfere with these.